As mentioned, I'm Zeb Weiss. I'm here to present our paper Root, Replaying Multi-Threaded Traces with Resource-Oriented Ordering. This is work I did with my fellow student Tyler Harder and our advisors Andrea and Ramsey Arpaki-Dusso. So to start out with, this is essentially an I/O trace replay tool. Why are we interested in this? Well, there may be other reasons, but the main reason we're interested in is for performance evaluation of new systems, essentially using it as a storage benchmarking tool. The advantage of trace replay in this particular area is that as opposed to, for example, a synthetic benchmark, which just kind of gives you a workload, using trace replay gives you much more a sense of your workload. So it really gives you a better picture of what your performance on a potential new system is going to be like. So as a starting point, we had a previous SOSP paper from my co-author Tyler. A file is not a file, you may remember. This gave us 34 system call traces of various Apple desktop applications, things like iPhoto and iTunes and so forth. We thought it would be an interesting challenge to try to replay these traces, and it might produce some interesting results. However, when we set out to do so, we found that it was not, in fact, quite so easily as simply replaying a bunch of traces. The primary source of difficulty was that modern workloads like this may complicate trace replay a great deal, and that they're heavily multi-threaded, in many cases anyway. And like so many other things in this field, threads make everything more complicated. So specifically in this case, interactions between threads have important effects on performance and correctness. On the performance side, you can easily imagine that things like differences in I/O completion order between one storage stack and another can easily affect performance in significant ways. For correctness, we can just look at an example. If you take this trace here, this is a fairly simple system call example trace. It's two threads, threads 1 and thread 2. We have thread 1 opening path 1 and path 2, providing file descriptors. Thread 2 reading from one of those file descriptors, then thread 1 closes file descriptor 3, and then we have navstat of file descriptor 4. This sort of sharing of resources between threads is a common pattern in these sorts of applications. So to make this easier to look at, we can just sort of split the trace into its component threads. So if you were to take this trace and perform sort of a simple, straightforward replay of it and not pay careful attention to exactly how you're doing it, you could easily end up with a somewhat different replay order. So for example, in this case, you end up with the read before the open. This doesn't cause any problems because there's no dependencies there between the system calls. Likewise, having open before the first read is also not a problem. Again, there are no dependencies. But there are orderings, for example, this one, that cause problems because you've now put a read of file descriptor 3 before thread 1 has created that file descriptor. So your read fails with ebadf instead of transferring the 1K of data you asked for. Likewise, if you have a use of file descriptor 3 after you close it, you have run into the same problem. This is, however, a fairly obvious example. Clearly, you can't use a file descriptor that's not safe to be used. However, there are more subtle problems that can arise. For example, in this trace, which might superficially appear simpler because in this trace we have no sharing of file descriptors between threads. As you can see, file descriptor 3 is strictly in thread 1, file descriptor 4 is strictly in thread 2. There is, in fact, a somewhat hidden dependency here. Not a problem with the opens or putting them right before the second open, but there is actually a dependency between the read and the write. If you reorder those, you change the semantics of the trace. The reason for this is that despite the fact that the read and the write are referring to different file descriptors, those two file descriptors in fact refer to the same file, path 1, that was opened in both open calls. And if you look at the first open, and you see it was passed O trunk. So that file is going to be a blank 0 immediately after that open. So if you put the read before the write, there's no data in the file for it to return, as opposed to in the original ordering, the write populated that file with data that the read then returned. So this is not actually as contrived a scenario as it might seem. This is something that we actually ran into fairly immediately on attempting to replay the ibench traces. It was a somewhat common occurrence, things like this. So given this problem, the obvious question is, how do we deal with this? One obvious, fairly simple answer is simply to preserve the ordering of the original trace during replay. This does give you the guarantee that you preserve the semantics of the original trace. You avoid any correctness problems like we saw in previous examples. But it tends to be a very pessimistic approach, and that limits the utility of the replay for performance analysis purposes. So to illustrate that, if we have this trace here, this one illustrates some overlap between system calls between threads. You see the green thread on the left doing small 4K reads, and the blue thread on the right doing larger reads. If we were to take this application that produced this trace and run it on a different system with somewhat different performance characteristics, you could end up with something like this happening, where the 4K reads, for one reason or another, complete much faster. So if this were the kind of natural behavior of the application, things would look like this. However, if you were to perform a replay of that original trace with the restriction that you're preserving the exact ordering that you had in the original trace, you can't really produce this behavior of the original application, because here you have the third green read on the left overlapped with the first blue read on the right, whereas in the original ordering, that green read was strictly after the first blue read. So performing an order-preserving replay, you're forced to insert this artificial stall into the replay in order to preserve the ordering. So you end up with these sort of artifacts of the timing of the original system where the trace was collected, kind of leaking into the timing of your replay on the new system that you're looking at. You don't really get a very good sense of what the new system's performance is actually like with your application. So our proposal instead is what we're calling ROOT, Resource-Oriented Ordering for Trace Replay. The aim of this approach is essentially to provide just enough constraint on the replay ordering to avoid correctness errors, like we saw in the first two examples there, but little enough constraint to allow things to order themselves naturally, as ideally the application itself would, so that you don't end up with weird timing problems like you had in the third example there that we just looked at. So essentially we're looking for a replay strategy that provides both correctness and realistic performance characteristics. So we've implemented this more kind of general root approach in a trace replay system called ARTC. We've evaluated it with a set of microbenchmarks that we devised for it, and also a pair of level D macrobenchmarks. We find that on our microbenchmark suite, ARTC achieves, in all four cases, within 6% timing error relative to the original application, whereas simpler replay strategies that we compare against are in some cases off by up to 600%. And on our level DB workload, looking at a system called concurrency, ARTC achieves 95% of that on our level DB workloads, whereas simpler replay strategies are as low as 60%. So for the remainder of the talk, I will go into some more detail on what exactly root is, how resource-oriented ordering works, detail our implementation, ARTC, and then go into some evaluation and results of ARTC in terms of performance and a more detailed look on how, at sort of a micro level, these performance effects end up happening, and finally some conclusion. So what exactly is root? We call it resource-oriented ordering. The resources we're talking about here, this isn't necessarily an exhaustive list. You could have different resources in different contexts, but the ones we're concerned with for file system trace replay are files, file descriptors, path names, and asynchronous I/O control blocks. These are, the ones we're interested in. You could take a more fine-grained approach, even in the context of file system replay, but these are the ones we find most relevant for our purposes. We have the property that not all of these resources appear explicitly in traces. For example, you'll never really see a file itself referred to explicitly in a system call trace. That, if it were to happen, would probably take the form of something like an inode number, but we generally don't have those. You see files referred to indirectly by things like file descriptors and path names. So we consider resources like that to be a different type of name resource that refers indirectly to the underlying file resource. And in the case of an AIO control block, we have the sort of interesting doubly indirect situation of an AIO CD referring to a file descriptor, and then that file descriptor then in turn refers to the underlying file. So with these resources that we're looking at, we have a set of ordering rules that we apply to them. Exactly which rules are applied to which resources is detailed on the paper. So our first kind of simplest ordering rule is what we call stage ordering. It's a fairly simple, intuitive concept. It basically just enforces that for every use of a resource, that use has to fall in between that resource's creation and its destruction. So this addresses problems like the use after close of the file descriptor we saw in the first example that looked sort of like this. So these resource ordering rules effectively kind of insert barriers into the ordering of the replay. So for example, in this trace where we had the problem before, applying stage ordering to file descriptors here would insert barriers somewhat like this. So that prevents the read from being reordered before the open or after the close. Second ordering rule is sequential ordering. This is a stricter rule that enforces that every access to a resource has to happen in replay in the same order that that subset of accesses happened in the original trace. So this addresses problems like we saw in the second example, where there was that more subtle dependency on the file size of the same file referred to by those two file descriptors. So in this case, the analogous barrier would be this, so that prevents the read from happening before the write and avoids the file size problem we saw earlier. Our third ordering rule is what we call name ordering. This preserves the ordering of different generations of a name resource. So this problems, if you avoid this rule, you can end up with problems with things like lock files. In a situation like this, where you have a file with some name, say foo, and you have two sequences in different threads of different generations of that name. If those end up overlapped, you can end up with problems either with, for example, in this trace, the create and the unlink failing. So the relevant barrier here would be one like that name ordering would insert to keep those two generations non-overlapping. So we've taken this kind of framework for trace replay ordering and implemented it in a replay system called ARTC. That's an approximate replay trace compiler. So now I'll go into what goes into the compiler, its inputs. Its main two components. We have a separate compiler and a replay engine, and ultimately the replay that it performs. So on the input side, we have from the source system where the traces are collected two inputs to the trace compiler. The first is simply a snapshot of file system metadata that gives you paths, file sizes, no actual file content, just what's necessary to create a file system tree that looks like that. And the meat of it is the system call trace, which for each system call gives you timestamps on entry and return, so we can see exactly how system calls were overlapped in the trace, which thread issued the system call, what type of call it was, its arguments, and importantly its return value, so that we can verify that the behavior of the replay matches the behavior recorded in the trace. So having collected those inputs, we feed them into the compiler, which parses through it all, extracts all the necessary ordering information and dependency information necessary for the rules discussed a moment ago. It compiles this all and encodes it into its output, which takes the form of C code. It's not code in the executable sense, it's merely a bunch of static data structures, basically just arrays of structs. And that ultimately gets compiled by whatever C compiler you have lying around into a shared library, which the replay engine then loads and replays. The system supports a bit over 80 system calls. It runs on 4 different operating systems: Linux, Mac OS X, FreeBSD, and Lumos. And so when we go to replay on one of those systems, the replayer, as mentioned, loads that shared library compiled from the compiler's output. It restores the file system metadata snapshot that the compiler parsed initially, spawns one replay thread for each thread that appears in the original trace, and then lets those threads run while enforcing the necessary synchronization to apply the ordering rules to the replay. It also, importantly, emulates unsupported system calls, which arises because, while all 4 systems that we support are essentially Unix systems, they all have their slight variations on the basic Unix API. Your common kind of meat and potatoes, system calls, open, close, read, write, and whatnot, those are all compatible, pretty much universal. But there are situations where you have system calls that are not supported on one system. So we have the ARTC replay engine emulating those with the best available approximation on the system you're running on. So same as that, on OS X, you have this sort of nifty operation exchange data, which takes 2 file names by path and atomically swaps their data, preserving inodes, which is sort of a unique primitive that other systems don't offer. So the best we can do is a sequence of a link and 2 renames that sort of approximates a similar effect. Likewise, we have a difference in semantics in fsync between, for example, in Linux, you have, at least with certain file systems and configurations, what I would call kind of a real fsync, where it flushes data from the hard disk's cache onto non-volatile platters, and thus has very different timing characteristics from fsync on Mac OS X, which does not perform cache flushes like that, and thus tends to operate much faster. Mac OS X instead offers a separate fcontrol call with semantics more similar to Linux's fsync. So if you had a trace collected on a Linux system and you were aiming to replay it on Mac OS X, you might enable emulation of fsync via this fcontrol command. Another situation is extended attributes, which are supported by all 4 of these systems, but in slightly different ways. So it performs the necessary translation to implement those. While this is enough of an implementation to be a useful benchmarking tool, it does have some limitations, most of which are essentially just side effects of inherent limitations of dealing with system call traces. When you only see system calls, you don't necessarily know all the details of application level synchronization. So we can't really guarantee that the ordering that the ARTC replay engine provides during replay is necessarily an actual ordering that the original application would actually have produced. But it's close enough for our purposes. We're looking at performance. Likewise, because we only see system calls, I/O performed via M-mapped files is not reproduced. But for the workloads we've looked at, the ibench traces and others, this isn't a big limitation because they don't make much use of that. So to evaluate this, we've compared it against 3 simpler replay strategies. Very simple single-threaded replay, which just uses one replay thread to replay all the system calls in the original trace, regardless of which thread they came from. What we call temporally ordered replay, which is essentially the order-preserving replay discussed earlier. It is multi-threaded. It has 1 thread per trace thread, but it enforces synchronization between those threads such that the ordering of the replay is identical to the ordering of the original trace. We also have a multi-threaded but completely unconstrained replay, which again uses 1 replay thread per trace thread, but enforces no synchronization or ordering constraints between them at all. So we've evaluated these 4 different approaches with 2 different criteria: semantic correctness and performance accuracy. On the correctness side, we look at basically just the return values of the system calls. If we see that open, or rather, read and write, transfer the same amount of data, we, interpret that as having preserved the essential system call semantics of the trace. On the performance side, we look at how well the performance of the replay matches the performance of the original application across different systems. So first, to investigate correctness, the workload we used was a benchmark suite called Magritte. This is essentially the result of applying the ARTC compiler to the ibench traces that we started out with. The reason we went with this particular workload is that these applications are very metadata intensive and heavily multi-threaded, which combines to give a somewhat less sound replay the opportunity to screw things up in many places. So a nice illustrative example from that ibench suite, or rather the Magritte compiled suite, is the iPhoto import 400 trace from those traces, which consists of a bit over 800,000 system calls. The simpler single-threaded and temporally ordered replays actually don't do quite perfectly here. They have 4 errors. These aren't, however, in fact due to ordering problems because we're preserving the same ordering. They're actually just sort of inherent problems in the traces themselves. There's a slight lack of information about extended attributes, which makes a kind of a fully correct replay not really feasible. In contrast, a fully unconstrained replay, as you can see, has vastly more errors. Almost half the system calls in the entire trace fail. You might kind of expect this given that it's completely unsynchronized. So upon seeing results like this, we eliminated unconstrained replay from further consideration. We didn't bother doing a performance evaluation on it because it's really just not preserving the appropriate behavior of the trace. ARTC, in this one case, does slightly worse than single-threaded and temporally ordered uncorrectness. We have 3 additional errors. This is actually the one case in the entire ibench suite where there is any correctness difference between ARTC and the simpler replays. This is due to a slight edge case in an unusual sequence of operations that occur in this one trace, that it doesn't quite handle correctly. This is essentially just kind of a minor implementation bug, but in all other cases, the correctness numbers are identical. So to evaluate the performance, we have our 4 microbenchmarks that we developed that investigate differences in disk parallelism between systems, cache size, one that actually makes no difference in the system at all and just simply replays the same workload on the same system. And finally, experimenting with different I/O scheduler parameters. We also have a pair of level DB macrobenchmarks that we use to later to investigate some of the kind of low-level details of how this ends up happening. So to start out with our disk parallelism benchmark, we have a trace that we collected of this workload, 2 threads doing random reads to large files on a system with a single disk. And then we ran that same application on a system with 2 disks in a RAID 0 array. So what you see here with this original bar on the left here is the timing of the original workload running on the new 2-disk system. And then the remaining bars we'll get to in a moment are replays, different trace replays of a trace taken from the original single-disk system running on the RAID. So for a single-threaded replay, runs substantially slower. This is perhaps, again, to be expected given that a single-threaded replay can't really achieve any I/O parallelism. The temporally ordered multi-threaded replay is significantly better, but is still noticeably slower than the original application running on the RAID. In contrast, ARTC is very accurate in reproducing the performance of the original application on the new system. So it sort of predicts its performance very accurately. For our cache size analysis, we have a similar workload, but one thread does a sequential read of its data to warm up the cache beforehand. And then we look at the effects of moving from the system with a 4 gigabyte page cache to one with about 1.5 gigabytes. We see somewhat similar trends of the simpler replays running slower than the original application on the new system. And again, ARTC does well at maintaining the performance, achieving good performance accuracy relative to the original application. So this is our special case of changing nothing about the system at all. And this just sort of illustrates with sufficient parallelism in your workload, in this case, perhaps even a somewhat modest 8 threads, then you can easily end up still with significant performance differences. We have ARTC, again, achieving much more accurate replay than the single-threaded and temporally ordered replays. This is a different case where the simpler replays vastly overperform, which we detail a bit more in the paper. It's kind of an interesting scenario where the replay essentially ends up preserving the original I/O scheduler's decisions during the replay, regardless of what the target system's I/O scheduler actually wants to do. So that's sort of a neat case. So to look at why this happens, we can look at dependency graphs between the different replays. So this is a slice of our level DB benchmark, a narrow slice of time. Each one of these nodes in this graph is a system call. Each line is a thread. For temporal ordering, we end up with this set of edges, which looks kind of dense. What actually matters, however, is not the density, is the length of these edges, rather in the x-axis. So for temporal ordering, we have an average edge length here of about 10 milliseconds, whereas in comparison, our ARTC dependency edges have an average length of nearly 9 seconds. So this graph is perhaps slightly misleading in that it only shows 2 edges. The reason for this, however, despite the fact that there actually are a lot more edges in this graph, because they're so much longer, they're vastly off the right and left ends of this narrow slice of time, so we can't really show them here. Having these much longer edges gives it vastly more flexibility in how it reorders the replay at runtime, which is where most of the kind of performance flexibility comes from. Look at how that kind of plays out in an actual execution. What we have here is sort of a similar view with 1 line per thread of an actual execution of the same workload. We have each kind of colored block here representing the duration of a system call. So we have the original application here, obviously being highly concurrent. We have very densely issued system calls across the entire span. We have about 3.9 outstanding system calls on average. If we perform a temporally ordered replay, we end up with this, which clearly doesn't look very much like that. We have all these stalls all over the place where we have the temporally ordered replay waiting on these kind of artificial dependencies that it enforces to maintain the same ordering as the original application. In contrast, an ARTC replay achieves this, which clearly isn't perfect. We still have some visible gaps there, but it's much, much similar, more similar to the original application than the more strictly ordered replay. So in conclusion, we have our simpler replay strategies that we've compared against that achieve good correctness results, but don't really give a useful sense of performance. And again, the unconstrained replay that we saw was nowhere near correct enough to really consider usable. Whereas ARTC achieves both good correctness results and gives you more of a meaningful sense of performance on your actual target system that you're looking at. So if you'd like to play with the code, we have this available for download at this URL. It's also in the paper, so you don't need to write it down or anything. So with that, I'll take any questions.
Easy, Marcos.
Oh, Marcos Aguilar, Microsoft Research. So you mentioned as a limitation that you don't track these dependencies that arise because of synchronization between threads. And I think there might be a bigger limitation than you suggested with your evaluation using Magritte. In particular, let's say you have utility to copy a file from one directory to another. If you have a thread that just reads the files from the source directory, and the second thread will take the contents of the files from memory and write in a second directory, all the synchronization and all the causality here is because of memory synchronization. And I think the correctness of your tool for that specific trace would be pretty bad, right?
Yeah, there are certainly workloads and patterns of thread communication that it wouldn't necessarily handle. As mentioned in the paper, there are other patterns, like for example, if you have like a pool of worker threads, what work ends up in what thread is something it's not going to be able to really predict as well. So there are definitely workloads where it doesn't necessarily handle everything correctly, but there are a lot of cases like these sort of applications we've looked at where it does handle things as well.
Jeff Kenning, Harvey College. I was a little confused about some of your ordering constraints, because at one point you showed us a slide that where things only worked if you ignored the original ordering, but then later you said that in order that you maintain the original ordering to satisfy some of the dependencies, and so I'm missing something here that I don't quite understand what ordering you are maintaining temporarily.
So we maintain a kind of a set of partial orders or orderings over certain subsets of system calls that access certain resources. So I mean, perhaps I misexplained something, but there's no situation where maintaining the original ordering is a correctness problem at all. It just tends to induce problems with timing, where it sort of preserves the timing characteristics of the system where the trace was collected rather than one you're actually trying to run on. So we aim to allow reorderings that maintain correctness but give you a better sense of performance without, running into problems like we showed in the first two traces, which were only problems if you don't if you're not careful about exactly what partial orderings you maintain.
Okay, so I have a question. I didn't see it in the talk or the paper, but it's more about motivation and concrete scenarios when you would want this. So the assumption is that the trace happens once in the field, let's say, and then you're going to replay. So what are concrete examples of when we would actually want to do something like this?
So if you have, an application that you're running on your production system and you're, evaluating some potential replacement system, you may want to, compare multiple potential replacements and see how they perform on your workloads. You can collect a trace of your running workload on your existing production system, replay it on whatever, potential replacement candidates you have, and see how they perform relative to each other on your workload, ideally.
But in that,
I mean, obviously, in some cases, you could simply run your existing workload on your target systems, but there are cases where that might not necessarily be feasible for licensing reasons or, not having correct input data to feed it at all times exactly, things like that.
Petros Pinatis, Intel. I was wondering if you could give me some intuition why ignoring memory mapped I/O doesn't affect your correctness. Some of the applications that you were talking about in the traces have pretty heavy memory mapped I/O. So why is it correct?
Well, I mean, again, the correctness that we're looking at is correctness from kind of a syscall API perspective. We're just looking to match the return values of the system calls we're replaying. Some of the iBench applications do use memory mapped I/O, but I think it, in most cases, is I think the sort of smaller fraction of it. And again, as I mentioned, in applications that do make heavy use of that, this will be less applicable. You could, extend the same sort of conceptual framework, and with a different implementation, you could do like a VFS layer trace rather than a system call trace. Apply the same sort of ordering rules and capture memory mapped I/O and implement a similar system that handles that. Our implementation doesn't happen to, but you could do that.
Thank you.
One final question. Have you explored extensions in which you take multiple traces that are collected and do a similar analysis?
No, we haven't.
Okay. Please thank the speaker.